This lecture is going to go through some localized winds, and you've probably heard of the phrase, "it's always cooler by the lake," when we talk about Lake Michigan. Well, that's an example of a land and a sea breeze. So we're going to identify that. We'll apply that to how and why that's true, but it's not always correct. So here we go. Small scale winds. These are produced from temperature differences with the land, and it could be land with other land, it could be land with water. But there are three types, and we're going to look at land and sea breezes. And by Lake Michigan, we call them lake breezes, and these are what occur locally. And these occur from Lake Michigan and the land having different specific heats. Therefore, they heat up differently. So this is going to change the high and low pressures. It's going to determine what air is rising and sinking. We're going to look at mountain and valley breezes, and we'll briefly look at Chinook and Santa Ana winds. But let's start off with the land and sea breeze. Land and water have different specific heat capacities, right? The amount of energy that they can that it takes to heat them to change their temperature 1 degree. So a sea breeze. During the day, the land heats up more quickly and forms low pressure due to rising air. So here's my sea breeze in my picture here. Sea breezes take place during the day. The air from the water sweeps in, leaving a sea breeze, cooling the surrounding shoreline. So in the summer, when the temperature of the land is greater than that of the water, you create this sea breeze. And this is localized. Along Lake Michigan, we call this a lake breeze. We get a lake breeze during the day. So on hot summer days, if you're over by the lake, you get this breeze coming off of the lake that's cooler. It's refreshing. So let's look at this one more time. Lower pressure, we've established air must be rising. Well, if this air is rising, you have to have air moving in to fill the void of the space that it had opened up from rising. So the cooler air is going to come from over the water. So this is going to be a cool, refreshing summertime breeze. But at night, everything switches. And this is called a land breeze. During the night, the process switches. Since the land cools more readily or faster at a greater rate than the water, air above the water is going to be rising. Here's your lower pressure. The water temperature is going to be much more stable. So we actually create a temperature differential. So the water, the air is going to be rising above it. This is your low pressure. And then the higher pressure is going to be air that's from the cooler land, right? It's going to change the temperature differently. So the water is going to be providing the low pressure, and the air is moving in from the land to the water. And the land cools to a temperature lower than the water, so the breeze switches in its direction. So at night, if you're standing on the lake, the land breeze here is going to come from, well, let's just say from the west towards the lake. But during the day, it's going to be a sea breeze. In our case, locally, we call this a lake breeze. A lake breeze is just a smaller scale sea breeze. But the process is based on find the low pressure, find the high pressure. Air always moves from high to low. During the day, land heats up more, low pressure over land. At night, lower pressures over the water. So we can look at that. So illustration of a sea breeze and a land breeze, and we can also call that a lake breeze. But over cooler water during the day, the air is going to be warmer. So we're going to heat up. It's going to rise, right? We've got convection taking place. It's going to rise. It's going to eventually cool and sink. So here's our low pressure or high pressure. Right? Remember, low pressure is going to be rising, and then the high is going to be driven. It's going to aloft. It's going to eventually cool. High to low, it's going to sink. So here's your high to low. And then at night, the process switches. At night, the water is slightly warmer. And it's not necessarily red, not red hot. It's going to rise. And so this is your low pressure. Rising air is low pressure. High pressure is going to eventually push the air towards low. It's going to sink. And the process starts over again. So this is what we're forming this pressure gradient force. Very important here. Let's apply a PGF. Where you have a pressure gradient force, you will find winds. Winds are always driven from high to low pressure. Another example is a valley and a mountain breeze. A valley breeze, and this is similar, but not exactly the same. Obviously, we're not using water, but it's very similar to the concept of a land and a sea breeze. So valley breeze occurs during the day. As air warms, air rises up the mountain slope due to convection. Where's my picture? Here we go. During the day. Rising. Air is rising. And cooler air falls into the valley, right? The cooler air is going to fill that void, creating a valley breeze. So here we get this nice convection cell here. Here we get this nice convection cell here. But a mountain breeze occurs during the night. And the mountain air cools rapidly at night, falling down the slopes. So here we have this convection cell creating the mountain breeze itself. So the base of the mountain itself, this is where your air is going to be rising. You're going to get cooler air traveling down the slopes. Right? The warm air is still rising. We still have a convection cell. We still have low pressure here. It's going to be rising. We have higher pressure pushing the air back in to fill its place. So here's your valley breeze during the day. Here's your mountain breeze during the night. Just find your high and low pressures. So this is what we call a Chinook wind. This is considered, phrase is referred to as a snow eater. Here's why. Cool, moist Pacific air masses drop out their moisture on the windward side of the Rockies. Right? We've established this. We've looked at this. We've quantified this with talking adiabatic cooling and heating. Well, this would be a cooling feature as an air moves over an orogenic boundary. As the air continues moving over the boundary, the air begins to descend and warm due to adiabatic heating, right? Compression. Well, this air can melt tremendous amounts of snow and ice in a very, very short amount of time, very rapidly, very quickly. So this Chinook wind is simply just adiabatic heating, but it's just named. And as this air continues to descend, it continues heating. So this can actually be pretty dramatic pressure changes. The pressure change of the air mass moves over an area can actually drive people to getting migraines, be restless in their sleep, irritability, dry skin, but these are only temporary. And this is actually, there are predictions as to when the Chinook winds are going to take place, and they can say, okay, get ready, you're going to be irritable for a while. And I guess it justifies people being crabs. But these pass on as the air continues moving over. So it moves on. It gets better. Here we'll move into the Santa Ana winds. These are referred to kind of locally from Californians as the devil winds in southwest California. And air is moved from high to low pressure. So high pressure, lower pressure over the ocean. Air around high pressure moves clockwise. We call this an anticyclone. So when there's a Pacific low, right, the low is out here in the Pacific, the pressure gradient force is created, pushing warm, dry air downslope, where it warms even further due to compression. So you already have warm, dry air, and it's going to continue to descend. It's going to even heat up even further. Well, so here's your high pressure system here. It's just showing you the same thing. Pressure gradient force is moving this way. And here's a picture of what this looks like. Wildfires spreading warm Santa Ana winds are partially responsible for spreading the annual fires in California. So these winds are considered katabatic winds as air flows downhill. So as it flows downhill along this particular slope, they heat up even more due to compression. So you can actually see these wildfires here, that the winds are the Santa Ana winds, the devil winds that are pushing the air out over the Pacific itself. So wind measurement. So there's two different types of measurement. Let's not overthink this. We've got direction and we have speed. The direction, the winds are generally labeled from where they originate. A southerly wind blows from the south toward the north. Don't overthink that. Southerly winds are going to bring warmer conditions. Northerly winds are going to bring generally cooler conditions. Think of where the air comes from. It's going to give us an indication as to what can take place in general. And an instrument for measuring wind is called a wind vane. This looks like this, kind of a general one. I actually have one on my house. I don't think it works though. I've never used it or looked at it. Maybe I should. So wind measurements, last but not least. So direction. This is indicated by either the direction in which it's pointing, right? It could be north, it could be northeast, it could be south, west, etc. Or you can use a degree value at the unit circle, the 0 to 360 degrees. Prevailing winds come more often from one direction. We live in the region of westerlies, so our winds we think of move from west to east. But very rarely do our winds actually are they out of the west. Now it happens, but it's not that common. So you have to be careful. You pay attention to what is taking place, and that's where we're going to be measuring using isobar lines and identifying the direction of pressure gradient force. And then lastly, speed. These are often measured with what's called a cup anemometer. That's what we see here. This calculates the wind speed by knowing the circumference. Right? I can just calculate the position of this circle, the average position of the circle, if I know its circumference. Right? If I know a radius, I can do 2 pi r. Circumference is 2 pi r. And I can see how long it takes to travel that one rotation in some unit of time. So if I got it in say centimeters per second, I could convert that into anything I wanted, miles per hour. But the idea is that it's a circumference, right? This is rotating, and the calculations come from the circumference divided by the time. All right, people, there you go.